Hello everyone and welcome to this video presentation. Today we are going to explore the foundational bedrock of all modern computing, the binary number system and the fundamentals of computer arithmetic. Have you ever stopped to wonder how a computer, which is essentially just billions of tiny electronic switches carved into a piece of silicon, can display beautiful high-definition video games, calculate complex financial trajectories, or process human language? At the lowest level, computers do not understand our letters, our decimal numbers, or our complex symbols. They operate entirely on pulses of electricity. To a computer, everything in the universe boils down to two states. Either electricity is flowing or it is not. A switch is turned on or it's turned off. Because of this physical reality, computers rely on a base-2 mathematically framework known as a binary number system. Understanding this system like learning the native language of microprocessors. And today we will break down exactly how it works and how computers use it to perform math. Okay, the first one is the decimal and versus binary system. To truly understand binary, it helps to look at the system we humans use every single day, which is the decimal system or base 10. The decimal system likely evolved because humans have 10 fingers, giving us 10 unique digits to work with 0 through 9. When we write a number like 300 or 45, we are using positional notation system, the 5 seats in the 1's place, the 4 seats in the 10th place, and the 3 seats in the 100th place. Each position moving to the left represents a power of 10. In stark contrast, the binary system in base-2 framework, meaning it only has 2 unique digits available, 0 and 1. In computer science, we call those 2-digit bits, which is sort of binary digits. Because binary is a base-2 system, the positional values do not multiply by 10 as you move to the left. Instead, they multiply by 2. The rightmost position in the 1's place, the next position to the left is the place, followed by the 4th place, the 8th place, the 16th place, the 32nd place, and it continues doubling infinitely. Okay, next is counting and converting in binary. Because of this unique layout, counting in binary looks very different from counting in decimal. When a computer sees the binary sequence 101, it does not see the number 101, and instead it decodes the positional values. The rightmost bit is a 1, which means we count one single one. The middle bit is a 0, meaning we skip the 2 place entirely. The leftmost bit is 1, which sits in the 4th place. By adding the 4 and the 1 together, the computer instantly understands that this binary sequence represents the decimal number 5. If we want to write a large number, such as 13, we simply look for the combination of our powers of to that add up to 13. We need 1 8, 1 4, 0, 0 2s, and 1 1. Therefore, the decimal number 13 is written in binary as 1101. Through this simple combination of bits, any number, no matter how massive, can be expressed perfectly using nothing but zeros and 1. Okay, next, computer arithmetic binary addition. Now that we understand how numbers are represented, we can look at the core of computer arithmetic, how computers actually do math. Let us begin with binary addition, which is the most fundamental operation performed inside computer central processing unit. The beauty of binary addition is that it follows a set rules. They are incredibly simple compared to decimal addition. There are only 4 primary scenarios a computer faces: 0 plus 0 equals 0, 0 plus equals 1, 1 plus 0 equals 1. The unique station happens when we try to add 1 plus 1. In binary, 1 plus 1 equals 2, But since the digit 2 does not exist in base 2, we write it as 1, 0. This means 1 plus 1 equals 0 when we carry a 1 over to the next position to the left. If a computer encounter a column where it has to add 1 plus 1 plus a carried over 1 from previous step, the result is 3, which is written binary as 1, 1. This means of bits a computer can add massive numbers less than a nanosecond. Okay, next, binary subtraction and to complement. Moving by an addition, we encounter binary subtraction, which introduces a major engineering challenge for computer. In human mathematics, when you want to subtract a number or represent a negative value, we simply put a minus sign in front of it. However, a computer hardware circuit cannot store a physical minus sign. It can still only store 0 and 1. To solve this, computer architects designed a brilliant system called 2's complement. 2's complement allow computers to represent negative numbers natively using binary digits, and it completely changed to subtraction work instead of building of complex, expensive subtraction circuit in the hardware. 2's complement allows the computer to turn a subtraction problem into an addition problem. For example, if a computer wants to calculate 7 minus 5, it transfers to expression into 7 plus negative 5. And then to create a negative number using 2 complement, the computer takes the positive binary version of the number, flips all of the 0 to ones and all of the ones to 0, and then adds a 1 to the final result. This inverted binary sequence acts exactly like a negative number when processed by the CPU. When the computer adds the positive number and this inverted negative number together, the correct subtraction result appears naturally. This is massive theorem of computer arithmetic because it means the exact same addition hardware circuit can handle both addition and subtraction seamlessly, saving vital space and power on the microchip. Finally, let us explore how the computer handles multiplication and division. In decimal mathematics, multiplication requires us to memorize extensive times table from 1 to 9. Binary arithmetic multiplication is incredibly straightforward because the only options are multiplying by 0 or multiplying by 1. Any binary number multiplied by 0 is 0, and any binary number multiplied by 1 just itself. Because of this, the CPU performs multiplication using a sequence of shifting and adding. In fact, shifting bits is so powerful that modern microprocessors use it as a shortcut. If you take any binary number and shift all of its bits one position to the left, you have instantly multiplied that number by 2. Conversely, if you shift all the bits of one position to the right, you have divided the number by 2. For complex division, the computer uses a repetitive process of shifting and subtracting the divisor form the dividing mapping out the quotient bit by bit. In conclusion, the binary system is computer arithmetic from the invisible language that powers our digital world. By reducing all human truth, data, imagery, and mathematics down to the simple contours between 0 and 1, computer achieve a level of speed and reliability it will impossible with any other system. Okay, thank you so much for your time and attention during this presentation. Bye bye.